Piecewise functions are kind of interesting because they combine everything that we've done with functions into one big thing. Piecewise functions, well, you can think from the name, piecewise. They're in pieces usually. And what it is it's a combination of two or more functions. But what makes these kind of interesting is that the rule, the function rule, is different for different parts of the domain. So we've been looking at functions where we might have a function, say, f of x equals x plus 2. And then we know that f of x is x plus 2 for all the real numbers, from negative infinity all the way up to infinity. What we're going to do now is we're going to look at a function where part of it might be x plus 2, but then another part of it might be represented by a parabola or some other function. So that's what we're going to look at in this video. If you haven't looked at the function, previous function videos, make sure you've done that because we're going to sort of put it all together in this. One particular piecewise function is the absolute value function. The absolute value function is where y equals the absolute value of x, or f of x equals the absolute value of x. What's interesting about the absolute value function is that it is actually a piecewise function. It's two lines that come together where one linear equation represents part of the domain and the other linear equation represents the other part. Now I just wrote down the parent absolute value function and you can see it graphed there. You can see that it starts at the origin and then it's two lines that have a slope of 1 or negative 1. So if I was going to write a piecewise function for this one, f of x is the absolute value of x, we can actually do it in two parts. Let's start with the left-hand side, the side that's less than 0. We can see that that is a line where the slope is negative 1 and the y-intercept is 0. So we would say that the function rule for that part of it is negative x. And that would be if x is less than 0. Now there's another half of the graph. We have the half that's going up. So for that one, that equation is another line with a slope of 1 and a y-intercept of 0. So we would say that function is x. And that's if x is greater than or equal to 0. So we can take that absolute value function and write it as a piecewise function. And you can see that there's one piece. That's part of the domain. And then the other piece is done on the other part of the domain. The absolute value function is so common that we have a special notation for it. But we can, split it up as we need to. While we're talking about the absolute function, I just want to point out a couple features of it. Just like all the rest of the functions, it fits in transformation form. So we might have the function y equals 2 times the absolute value of x minus 1 plus 3. And here's what this means. This has a vertical stretch of 2. It's been shifted right 1, and it's been shifted up 3. And we can graph this using our transformations, just like before. We don't even have to put it into piecewise form because it is that special absolute value function. And while we were talking about piecewise, I thought we'd talk about absolute value too. So I'm going to go ahead and graph this on that chart with the parent function on it. It says that I've shifted right 1 and up 3. So now right 1 up 3, that's where it starts. Since it has a vertical stretch of 2, normally the slope for each component is 1 or negative 1. Since it's a vertical stretch of 2, it's going to be 2 and negative 2. And go up, up, make my little v function, and there we have it. We can also, of course, do other ones, so we could also graph y equals negative the absolute value of x minus 2. And this graph has been reflected, and it's been shifted down too. So when we graph this one, it's going to start down there at 2, and it hasn't been stretched at all, so the slope is going to be negative 1 and 1 again. But because it's been reflected on this side, the slope becomes positive 1, so there's that branch. And on this side, the slope flips, and it becomes negative 1. So you can see that we really did piecewise functions here, but because it's the absolute value piecewise function, we can write it as one function rule. Not all functions are fancy and nice like this, so let's look at some examples. So here we have a piecewise function that's already been graphed for us, and you can see that it's a piecewise function because it has two different pieces to it. So it looks like we have two lines here, two distinct parts, so our function, our piecewise function, is going to have two rules to it. So I'm going to get it started so I can start filling it in. If f of x equals, now I'm going to start out with this left line, and since it's a linear equation, we need the slope and we need the y-intercept. We look at the points that are nice on this graph. It looks like we go down 2 and over 1, so our slope is negative 2. That means our rule is going to start with negative 2x. Now it also has a y-intercept at negative 3, so we can say negative 2x minus 3 is the rule for that part of the graph. But it's not the rule on all x's, it's only the rule on a few x's. So we need to be sure that we include that when we write our piecewise function. They start at negative 5 and they go up here to 0. Now at negative 5 it's a closed circle, so we could say that negative 5 is less than or equal to x, because we have a closed circle there. But at 0 it's open, so we would say it's just less than 0. So for all those x's between negative 5 and 0, including negative 5, the rule is negative 2x minus 3. But we have a second part to our graph as well. We have this other line here. So again, I'm going to look for a few nice points. I see them right there. Looks like I go down 1 and over 3. So the slope for that one is negative 1/3. And again, we can see the y-intercept, so it's going to be 4. And this one is only for the x's between 0 and 6. That's the only part of that line that we care about. Since both of them are closed circles, we're going to use the less than or equal to signs for both. So I would say 0 is less than or equal to x is less than or equal to 6. And that's the piecewise function for that particular graph. Now, it's important to be able to write what the domain and range are of your piecewise function. So we're going to look at those, because even though we have a couple domain and ranges listed in our piecewise function, if I wanted to write the domain and range of the whole thing, we would have to look at the whole thing as one big picture. So for the domain, and I'm going to use interval notation because I really like interval notation. We see that our function starts here at negative 5, and it's a closed circle, so we have a bracket and negative 5. Then as we move to the right, it looks like I stopped at 0, but is there a function rule possible for 0? Yeah, the second one. So we don't actually stop, we continue on all the way up to 6. So the domain for this function is negative 5 to 6. The range for this function is, well, let's start at the bottom, negative 3. However, negative 3 is an open circle, so it's not included, so we go negative 3. And then you proceed up, and you think, do I ever stop? Nope. I do have some overlap, but that's okay because we don't have to write overlap in our domain and range. We don't actually stop at 4. The whole function goes up all the way here to 7. So we would say that our range is negative 3 to 7. And I'm going to use a bracket for the 7 because it's included. So there we have our piecewise function for the graph, as well as the domain and range of the whole function itself, the whole function f of x. Now, there are a couple types of functions, piecewise functions. There are continuous piecewise functions and discontinuous piecewise functions. For us, continuous is something that has no breaks or gaps. But a discontinuous function is one that does have a break or gap. And it's pretty clear from this one that it is discontinuous. Discontinuous, I think I spelled that wrong. because there are two different parts. They don't continue flowing into each other, and so it is discontinuous. I would have to lift my pencil. Alright, that's enough for that one. Let's move on to another example. This function is a little bit different. It actually has three parts to it. You can see that we have a line, we have a parabola, we have another line. So we're going to have three parts in our piecewise function, and you can call it whatever you want. I'm going to call it g of x, just to mix things up. And we know that we're going to have three distinct parts, so I'm going to make my little brace a little bit bigger. And we need to write an equation for each of these parts. So I'm going to start out with the line. Now, when we write linear equations, we need the slope and we need the y-intercept. And if we looked at our linear equation right now, we can't actually see what the y-intercept would be. However, if you continued your line a little bit further, you can see that it would go through the point 0, 2. So our y-intercept is 2. Now, we need to have the slope as well. So I see there's a point at negative 2, there's a point at 2, so the slope is going to be up 2 over 2, or 1. So the equation for this line is x plus 2. And I know you're thinking, but the plus 2, it's not actually part of the graph. You're right. And that's where the particular domain is going to come into play. We need to say, well, what are the x's for this for which it's true? Well, this graph goes on forever. You'll see a circle if it doesn't go on forever. And in this case, well, we're going to start at negative infinity, and we're going to go all the way up here to where it stops, which is negative 1. So for all of the x's that are less than or equal to negative 1, this rule is true. Alright, so let's move on to the parabola. If we're looking at our parabola, we want to think about transformation form when we write our function rule. So it looks like we go over 1 up 1, or over 2 up 4. And that's the correct rule for a parabola that has not been stretched. Since it starts at the origin, we know that we just have x squared. But it's not a parabola forever and ever. We have to include, well, where is this parabola true? Well, it looks like this parabola is true from negative 1 all the way up to 2. Now that closed circle kind of makes it a little wonky because I don't know if the closed circle went with the line or if it went with the parabola. For this case, it doesn't matter. It gets us the same value, so I included it with the line. I'm not going to include it with the parabola. However, I do need to include that too. So from negative 1 all the way up to and including 2, the parabola is the true rule. Now we have one last line, and that's a flat line. So think about what a flat line represents. Flat line has no slope, or, well, it does have a slope. The slope is 0. So we don't have an x term in that. In fact, if you look at your flat line, our flat line stays at 3 the entire time. So for all the rest of the x's in this function, it's just 3. You say, hey, what happens when x is a million? Oh, it's 3. So for all of the x's that are greater than 2, because of that open circle, all of the x's that are greater than 2 are the ones that we include for 3. So there we were able to write our piecewise function, all three parts of it, just by looking at the picture and using what we already knew about those basic functions. Now let's find the domain and range of the whole picture, the whole g of x. And again, I'm going to use interval notation because it's easier. We can see that we started down here at negative infinity, and we traveled, we didn't stop, keep going, looks like we stopped, but is there a rule where 2 is true? Yes, there is. So we keep going, and it's all the way up to positive infinity. So our domain is negative infinity to infinity. Now we need our range. Now we got to start at the bottom. And again, this line is going on forever, so the bottom of the graph is negative infinity. And then we go up, and we don't stop at 3. It looks kind of like we do, but remember we have a whole bunch of 3s, so we keep going there at 3. We go all the way up to the top of the graph, which is here at 4. Since it's a closed circle, that 4 is included. So our range for this graph is from negative infinity all the way up to 4. And again, we would say, is this continuous or discontinuous? Well, it starts out looking continuous, but there is a gap. Because of that gap, we're going to say that this is a discontinuous function. I'm not even going to bother to try to spell it this time. What's kind of cool about piecewise functions is that you don't always have to consider the graph with them. Sometimes all we have to do is evaluate based on our piecewise function. So I could ask you, hey guys, what's g of negative 10? Now, when we had our other functions, it was easy. You knew what to plug it into. But in this case, we have to do a little bit of thinking. If I'm finding g of negative 10, I have to go, well, which of the three rules do I look at? And in this case, negative 10 falls in that first rule, the x plus 2. So if I want to find g of negative 10, I have to plug x in there. So that's going to be negative 10 plus 2, which is negative 8. And you could probably see if you continued your line down further and further, it would be down there at negative 8. Piecewise functions have a lot of applications, in fact, a lot more than just a regular straight function, because life works that way. While life isn't nice and pretty and in perfect parabola all the time. So here I have a graph that shows distance and time. So this is a graph that you might experience in physics, or if you were doing some testing with something that you built in engineering. So let's go ahead and write the piecewise function for this particular graph. And let's go ahead and assume that our graph stops here. I know it doesn't say it stops there, but I think that we're gonna use stopping points for this particular vehicle. All right, so I'm gonna call it d of x because we're talking about distance, right? And it looks like we have 3 distinct parts, so I'm gonna make sure I have enough room for all 3 parts. Now they're all lines. This is kind of not too bad because all we're gonna have to do are some linear equations. The first one starts out okay. Looks like it has 0, 0 as the y-intercept, so all we have to do here is find the slope. Here, since this is an actual application, we need to be really careful about the scale. Looks like I go up 40 and over 30. So the slope of this one is 40 over 30, which is 4/3. I want to keep it as 4/3 because if we put that into decimal form, it would be a repeating decimal and we don't like those. So 4/3 x is the rule for that part of the graph because we know that it would be plus 0, which is extra information we don't need to add. So I want to say, well, this rule is true from 0 because it's not going to have negatives. So this rule is true from 0 all the way up to time is 60. So from 0 all the way up to 60, this x is true. And again, that 60 is a little bit wonky, and I'm going to go ahead and put it with this one because it is the exact same value if I evaluated it with the second rule as well. And this is the function I'm using. So now let's look at that second line. This line has a negative slope. And I can't see the y-intercept, but that's okay. We can still figure this out. So I'm going to start out by looking for the slope. Looks like we go over, that was weird. Looks like we go over from 60 to 90. So we go over 30. And we go down from 80 to 20, which is down 60. So our slope is negative 60 over 30, which is nice, and it simplifies to negative 2. So the second part has a slope of negative 2. But I don't have the y-intercept. I can't see the y-intercept. So what I'm going to do is use point-slope form. Remember, point-slope form is where we know the slope and a point. It looks like I have a couple points on my graph. I'm going to choose this one. 90, 20. So if I plug this into point-slope form, I'm going to have, well, y equals negative 2 times x minus 90 plus 20. You can leave it in point-slope form if you want, or you can convert it to slope-intercept form. If we were to convert it, we would need to distribute. So we get negative 2x plus 180 plus 20. and then combine like terms. So we would get negative 2x plus 200. Which sort of makes sense if we look at our graph. It's going to hit the y-axis at some point. It's going to hit it way up there at 200. So that's the rule I'm going to use because I happen to like slope-intercept form. So negative 2x plus 200 is the rule for the second part of the graph. And that part of the graph is going to go from 60 to 90. So from 60, and I'm not including it because I already included it in the other one, all the way up to 90. Now we have one last part that we need to consider, and that's that final part of the graph that's going up. So if we look at this one, we have a pretty steep slope. It looks like we go up from 20 to 100, and so that is going to be 80. And we go over from 90 to 120, which is 30. So the slope for that one is 80 over 30, or 8/3. I'm going to keep the slope as 8/3 because, again, it's easier to deal with a fraction than a repeating decimal. That way we get an exact number. Now we would also want to find the y-intercept for this one, so we're going to use point slope again. I'm going to include the point 120 and 100. So we're going to end up with, I'm running out of space, y equals 8/3 times x minus 120 plus 100. And I'm going to do some distribution in order to solve this one as well. I'm going to distribute that 8/3 because I want to get it into slope-intercept form. So this is where you might need to get out a calculator because you're going to have to find 8/3 times 120. So we're going to have y equals 8/3 x minus 320 plus 100, which when we combine like terms is going to be 8/3 x minus 220. And again, look at your graph. Obviously that line is going to hit the y-axis down at some negative number. And this is true from 90 all the way up to 120. So there we have it. I know that was a little bit more work and you thought, oh, this is going to be easy, it's all lines. But we had to consider just those parts of the domain, and we also had to do some investigating, some solving for those y-intercepts. I'm not going to ask you to find the domain and range of this one. It's actually pretty easy. It's just the graph itself. And this one is interesting, though, because it is actually continuous. The graph doesn't have any gaps or breaks in it, so that makes it a continuous function. So whatever this vehicle is, it's going. This is a kind of cool graph that can be done a lot of different ways. And I want to do this one because we're going to use a little shortcut, a cheat, and we're going to use our absolute value function on this one. So we have a bunch of different parts, and as we move along the domain, we'll figure out how many parts we want to include. So I'm going to leave a big old bracket for all my parts. That's not a bracket, but it's close enough. Alright, so let's start out with that first little line. That's a line that's going down 1 over 1, and it has a y-intercept of 1, so we would say negative x plus 1. And that's for all the x's from 0 up to 1, but it doesn't include 1. So we have 0 is less than or equal to x, which is less than 1. Now if we look at this next segment of our graph, this is just a line. It's a flat line. And remember what we had with our other flat line. It's just that number for that part of the domain. So it's just 1. And it's 1 all the way from 1 to 2, but not including 2. So we would say 1 is less than or equal to x, which is less than 2. Now, there's that sort of random dot up there. We look at that. That means at 2, it's 2. So if we need to include this in our piecewise function. We would say, okay, the function is 2 when x equals 2. And that's it. It's a point. It still needs to be included. It is part of the graph, so it is part of our function. Now, if we go a little bit further, we can see that we have that v thing going on. So this is where, like I said, I wanted to cheat a little bit and use our absolute value. Let's practice that part. So here we have our absolute value graph. And the slope is 1 and -1, but it's been reflected down. So we know we're going to have a negative. We also look at how it was shifted. It's at the point 3, 2. So if we wanted to write an absolute value function rule for this part, we would say negative absolute value of x minus 3 plus 2. That shows that it's been shifted over to the right 3, and it's been shifted up 2. Now this absolute value is true from 2, but not including it, all the way up to 4. And it does include 4, so I need to use a less than or equal to. Now clearly this is a discontinuous function. However, we can still find the domain and range. So let's go ahead and do that on this one since we have all this extra space. So the domain, remember, is going to be the x's. So I'm going to start here at 0, and then I'm going to continue until I actually stop. Now, we don't stop at 1 because there is a place where 1 is valid. We don't stop at 2 because there is a place where 2 is valid. And we go all the way up to 4. So we would say that our domain is from 0 to 4. Sometimes your domain has a break in it, and so you would need to have a union sign. But again, we already did interval notation, so we're all good with that. So let's look at our range. Our range starts down here at 0. However, it's an open circle at 0, so we don't include it. So that would be 0 with a parentheses. Now, as we move up our graph, we don't stop at 1 because there are places where the graph is valid at 1. Keep going, and it looks like 2 is the highest value. Since 2 is valid, I'm going to use a bracket there, a little closed, like for a closed circle. So our domain for this graph is 0 to 4, and our range is 0 to 2, but not including that 0. And this is another example of where you could do some evaluation. So I could ask you to find, say, f of 2. That would mean, okay, well, that means x is 2. So I got to find out which function I use. And that's that fun one where x just straight up, or y just straight up equals 2. So we say f of 2 is 2. I could also say, okay, well, what's f of 1/2? Now, okay, where does 1/2 fit? 1/2 fits in that first function. So we would say, okay, well, that's going to be -1/2 plus 1, which is 1/2. So there you can see why it's important to have those domains listed for each part of your piecewise function so you know which part of the function applies for which evaluation you're trying to do. For all of the problems we've done before, I've given you a graph and we've written the piecewise function for it. Now we're going to start with a function and we're going to actually draw the graph. So this is 3 parts to it, so we're going to have 3 distinct parts in our piecewise function. And here's where those domains are going to be really important. It says x is less than 1, and I'm going to have -x plus 2. You can do this a couple different ways. You can think of the line as a whole, or you can actually just plug in some values. Let's try plugging in some values for this one, and then we'll do the other one the other way. So if x is less than -1, this is true. So let's start, or if x is less than 1, that's true. So I'm going to plug in 1. Well, that's going to get me -x, or -1 plus 2, which is 1. So at the point 1, 1, I'm going to have an open circle. Now this is for all the x's less than 1, so I'm going to go to 0. That would get me -0 plus 2, which is 2. And if we continued on, we can see that we have that line with a slope of -1 that goes through the point 2. Now, I could have done this one a little bit faster if I would have just graphed that line, but again, I wanted to show you the different options you have. So, done. Check. We did the first one. Now we're going to graph the second part. It says f of x is 2 from 1, including 1, all the way up to 5. So, at 2, I'm going to put a closed circle. And then it stays 2 all the way up to 5, but not including 5, so it's an open circle. There's my line. Not too bad. Now the other one is 1/2 x plus 1 for all of the x's that are greater than 5, and not including 5, remember. So for this one, we need to think about this a little bit. If we wanted to start with the line and then just make sure we included just the part that counted, we would have a y-intercept at 1, and we would go up 1 over 2, up 1 over 2, up 1 over 2. But you can see that those first few points that I drew don't actually count. In fact, we're going to have to start only here at 5. So there's that point at 5. And now I can actually make a solid line for my graph. So there you can see I could have just plugged in 5, 6, 7, and so on and so forth. But for this one I chose to use what I knew about linear equations to actually draw the graph. I don't care which way you use, whatever you're comfortable with. This is definitely a discontinuous function because there are gaps. There are breaks in this function. However, we can still find the domain and range of this particular function. So let's start out with the domain. Well, over here we have negative infinity. And then we keep going on our domain. We don't actually stop at 1 because 1 is included. However, what happens when we get to 5? It's not included in the second function, and it's not included in the third function, which means we have to stop. Our domain stops at 5, and it's not included. But it does start up again right after the 5, so we are going to have a union for this, and we're going to include 5 to infinity. Now the range for our function, let's see if we have any problems here. We start down here at 1, and it's not included, so I need to use a parentheses. Then I go up, and I don't think I stop ever. It's because of that red graph. It just keeps going on forever. So 1 to infinity is my range for this graph. Sometimes that happens where one part just overtakes everything and makes it a little bit easier for finding the range. Cool. So here we have two parts in a piecewise function that are both lines, and we can go ahead and graph them. It looks like these lines split at 0. So I'm going to use the slope-intercept form to help me draw my graph. I'm going to start with that first one. So I know that I have negative x plus 2 for all the x's that are less than 0. So I'm going to start with that y-intercept of 2, but since 0 isn't included, I'm going to keep it in open circle. Then the slope is negative x, so I'm going to go over, and there's our first part of the graph, all the way over to negative infinity. Now the second part does include 0, so when I use this one, the y-intercept is going to have a closed circle. So it looks like the y-intercept is 2. I go up 1, over 1, up 1, over 1, up 1, over 1. And there's our piecewise function. That should look familiar to you. That's actually an absolute value function. So here's an example of how those absolute value functions are piecewise functions in disguise. We could have also written this by saying, oh hey guys, f of x is actually equal to the absolute value of x plus 2. How was I able to write that so fast? I just used transformation form. The slopes were negative 1 and 1, and it hadn't been shifted left or right, it had just been shifted up 2. We can find the domain and range for this one too if we wanted, but those are actually going to be pretty quick and easy. If we look at our graph, our domain is just negative infinity to infinity. And our range, well, the bottom of the absolute value is 2, and it goes up to infinity. We could also evaluate this thing if we wanted to. We could actually find, say, f of 10. Again, you go, well, which part do I use? I'm going to evaluate it using the original piecewise function. For 10, we're going to use that second one there. And so we're going to say, oh, it's 10 plus 2, which is 12. You could also evaluate this one using the absolute value. The absolute value of 10 plus 2 is equal to 10 plus 2, which is also 12. One other kind of cool thing we can say about our absolute value function is that it is a continuous function. There aren't any gaps or breaks. At that 0, it looks like it stops, but it is included in part of it. We never ever stop, so it is a continuous graph. Graphing does get a little tedious, so for the next few examples, all we're going to do is practice some evaluation. So here we have the function f of x, and it's comprised of a parabola and a line. And we're going to do some evaluating with f of x. Let's find f of 0. So we go, okay, well, where is 0 included? here I have x is less than 1, and here I have x is greater than or equal to 1. Well, 0 is smaller than 1, so we're going to use that function to evaluate it. So f of 0 is going to be 2 times 0 squared minus 1, which is 2 times 0 minus 1, which is 0 minus 1, which is negative 1. Cool. Alright, so let's say we had f of 1. Well, here we have to go, okay, which function do we use? Sort of looks like we want to use the first one, but look, 1 is not included. 1 is only included in the second one. So for this one, we're going to plug it into the second one. We're going to have 1 plus 4, which is 5. So now let's do some evaluating with this function g. This function g has 3 parts, so we need to be extra careful. Let's start out with negative 2. Let's find g of negative 2. So where does negative 2 fit in our domain? Looks like it's the first one. The second one only is from 0 to 1, and the third one is for all those bigger numbers. So g of negative 2 means we use that absolute value. So we have to find the absolute value of negative 2. Remember, absolute value is just like magnitude, and so we're actually finding how far is negative 2 from 0. So the absolute value of negative 2 is just 2. So there we have it. G of negative 2 is 2. If we had a graph of this, we would see that point, negative 2, 2. All right, let's find g of 0. It looks like we're going to use the second one there. G of 0, well, it says g of x is 1 if it's from 0 to 1, and so 1. Done. All right, now let's find g of negative 10. So again, you want to look in your domains. Where is negative 10 included? Well, it's certainly not greater than 2, and it's not between 0 and 1. It's not between negative 2 and 0 either. So for this one, there's no solution. The function g does not exist where x is negative 10, and that's okay. So this is the last example, I promise. I just want to look at a couple more places where we might be tricked. Let's use this function h, and we're going to do some evaluating with h. Let's find h of negative 100. So now we have to think about which part includes negative 100. X is less than negative 2, or x is greater than negative 2. Well, negative 100 is less than negative 2, so we're going to use the first function. So h of negative 100 is negative 100 plus 3, which is negative 97. Alright, well let's flip it around and let's find h of 100. Well, now we go, okay, well, that's going to be greater than negative 2. 100 is definitely greater than negative 2. So now we're going to plug 100 into that. Looks like that gets us negative 200 minus 3, which is negative 203. See, good thing we didn't have to do this graphically, right? Negative 203. Yuck. Alright, let's try a smaller number. I've been giving you all these big ones. Let's find h of negative 2. Well, the first function applies for all of the numbers that are smaller than negative 2. And the second function applies for all of the numbers that are greater than negative 2. But no functions apply for where x actually is negative 2. So for this one, we have no solution. This graph does not exist. There's no point on this graph. There's no point in that whole domain when we were writing those whole domains where x is negative 2. And that's okay. No solution. So just sort of to recap what we did, we talked about piecewise functions, which are 2 or more functions, or 2 or more rules in one function, and it's for different parts of the domain. So one rule might apply for a few of the x's and another rule applies for some of the other x's. And we have a special kind of piecewise function, which is the absolute value function. The absolute value function is actually one of my favorite functions. It can be written as piecewise functions, or you can use the absolute value function, and transformation applies to it just like it does to any other parent function. Remember that the parent absolute value function is y equals the absolute value of x. absolute value of, say, a number refers to its distance from 0. So the absolute value of negative 10 is 10. So like the absolute value of 10 is also 10. What about the absolute value of 0? So how far is 0 from 0? It's smack dab right there. Awesome. So the absolute value function is a special type of piecewise function. Now we want to make sure we remember when we're doing these things that we consider domain and range of the whole function. I'm writing this out because it's important. So if you were asked, what's the domain of this? You can't just look at what's listed on the side. You have to actually look at the whole function to see if there are any overlaps. And when we do our domain and range, we usually use interval notation. And then the last thing I want to remind you guys about is the fact that we have continuous and discontinuous. So remember, continuous, there's no gaps or breaks. It just continues on. And for discontinuous, there are gaps or breaks. So I'm going to write that one, gaps and breaks in the graph. Now, it's important to note that continuous doesn't mean it goes on forever, from negative infinity to infinity. It just means that for the particular domain that applies to that function, then it is continuous. There's no gaps or breaks. That's why I only wrote down the definition of discontinuous, because then you can go, well, if it's not discontinuous, it's continuous. So that's our little recap, and we just did a whole bunch of piecewise functions. Hooray!